Alright, welcome back. Previous video we went over and established what the definition of a derivative, and we will look to explore in much more depth the derivative as a function in this video. So first, I don't want to write capital, but f of x is differentiable on some interval a, b, if f prime of x exists for all x in AB. That is the domain of f of x. Going to be a very critical definition for this video. Asterisk it, maybe box it, write it in a different color. Some notation that we can get out of the way. Leibniz notation. So we've been using this, primarily this f prime. If we were to take a second derivative, right, we would do another tick mark for double prime, triple prime, so on and so forth. But two alternative ways that we can indicate we're taking the derivative, or we have a derivative that we are working with, is df, but the vernacular is df dx, dy dx, right? The derivative of the function, remember y is, a sub way of writing the function, so derivative of the function with respect to x, right? This is the variable that we were actually deriving. And as I said in our last video, right, we're slowly going to make our way to the fun stuff, so a little quicker than expected, but the power rule when it comes to differentiation, this says that for all exponents, and if we take the derivative of the function, so the derivative of x to the n with respect to x, that is equivalent to n times x to the n minus 1. So what we're doing in essence as we derive this is we're taking the exponent, it now becomes a coefficient, and we're subtracting the exponent by 1. So linearity rules that we need to also establish before we can continue on include sum and difference rules, which say that if you have the sum or difference of two functions that you want to take the derivative of, you can separate the derivatives of those two functions and then add or subtract them, in addition to our constant multiple rule. This one's a good one to always have in your back pocket, which says if we have a constant times a function that we want the derivative of, we can multiply the derivative of the function times the constant, because remember, the derivative of a constant is 0. So let's get into some application, because this is going to be another 2-part video. The beginning of derivative is extremely comprehensive. So let's say we're tasked with finding the points on the graph of f of x equals x cubed minus 12x plus 4, where the tangent line is horizontal. And this is what I was talking about in the previous video, where yes, you can say that you can take the derivative of x squared, that you can take the derivative of sine x. Once again, here you're going to be required to take the derivative. However, if all you can do is just take derivatives, that's all you can do in this problem, and you really have zero clue what's even asking. So the foundation of derivatives is essential to success. So the reason why, because it doesn't even say to take the derivative, right? We're in the derivative chapter, thus we know we need to take a derivative. But the biggest keyword would be here, tangent line, right? The slope of the tangent is equivalent to the derivative. So this is why we will take the derivative using the power rule that we had just established. Right, so we have x to the third power, the exponent becomes a coefficient, we subtract 1, and same for the remainder of the polynomial. For the constant, derivative of a constant is 0, so excellent, we have the derivative here. Now, what does it mean graphically when we have a horizontal line? Well, it means that the slope is equal to 0, and if the derivative represents the slope of the tangent line, if we set this equal to 0 and solve, we come to find out that the x-coordinates, because that's what we're looking for, are positive and negative 2, where the tangent line is horizontal. But if we wanted to find those specific point values, we should substitute them back into the original function. So 2 cubed is 8, minus 24, which is negative 16, plus 4 is going to be negative 12. And negative 2 cubed is negative 8, plus 24 is going to be negative 6, or positive 16 plus 4, and that's 20. That I went over pretty quick because that's just quick arithmetic. But once again, it stems back to a solid conceptual understanding of these topics in order to be successful, because when you get to an exam or you get deeper into your mathematical career, there are no roadmaps, there are no bright electronic blinking signs that say, hey, do a derivative here. So the reason why, once again, that we know that we needed to derive and set equal to 0 is because of this idea of a tangent line, and that the derivative is a slope of a tangent line, and if the tangent line is horizontal, it means that there is no vertical change. The slope is 0, so set it equal to 0 and solve accordingly. We will do one more before we conclude this video. And once again, very difficult stuff, very comprehensive stuff that we are doing. So take your time. If you need to rewind the video, please do so. How is the graph of f of x equal to x cubed minus 12x squared plus 36x minus 16 related to its derivative f prime of x equals 3x squared minus 24x plus 36. Right, so we have a cubic and a quadratic. That should be a dead giveaway. So negative 16, 2, 3, 4, 5, 6, 7, 8, 9. We cross at 4, 8, slightly before, and we hit a max, and some mins. And how does that segue into the graph? So this is f of x. Let me do f prime of x in a different color. One, 2, 3, 4, 5, 6, 7. So let's examine. If we take a look at the original function, right, we can see that the original function has horizontal tangent lines at x equals 2 and x equals 6, okay, which means that their slope is equal to 0. Now if we look at the derivative, what's happening at those two values, okay, at those two values, the outputs are 0. Okay? So the intercepts of the derivative become the maximum and minimum values, hint hint, of the original function. Now, if we were to, draw in some dotted lines for our positive slope tangent lines, we can see that from 0 to 2 and from 6 onwards, the slope of the tangent line is positive. How does that look? How does that reflect on the graph of our derivative? Well, from 0 to 2, right, so this interval here, we can see that we have a positive output, and then from this interval onwards, right, to infinity, we also have positive outputs. So we can say that from 0 to 2 and x greater than 6, we have positive tangent slope, which leads to positive outputs. And it works interchangeably, right? If we're given this graph and we can see that, oh well, the slopes are, the outputs are positive here, that means my graphs should be increasing on those same intervals. We also talked about x equals 2, x equals 6. We have horizontal tangents, which become the x-intercepts. And the last piece of information, obviously, we left out is this interval between 2 and 6. We can clearly see the tangent line has a negative slope, and between 2 and 6 here, we can see that the outputs are negative. So 2 to 6, we have negative slope, which yields negative output. Okay, this piece is a lot to absorb, so you might want to go back and rewatch that segment. Okay, remember, the outputs here dictate the slope of the tangent lines, which inform the behavior of the function, whether or not it's increasing or decreasing. If we have positive outputs on whatever intervals, that leads to increasing behavior on the function, on the original function. If we have negative outputs, that leads to decreasing behavior on the function. And then if we have intercepts on our derivative, that equates to horizontal tangents, which thus implies maximum and minimum values on the original function. That is where we'll take a 30-second timeout and pick it up with part 2.